Welcome to the video on the properties of solutions. Alright, so we now want to examine the thermodynamics of the mixing of liquids. So we have two pure liquids and we're going to mix them together. And so we're going to start with our simple case of an ideal solution. So now we're going to see the consequences of molecules of one species intermingling randomly with those of another species. So what's going to happen to the entropy here when we mix our two pure liquids together. So we'll then be able to examine deviations from our ideal behavior by actual real solutions. So first we're going to look at the ideal solutions and then extrapolate from there to real solutions, so differences. Alright, so the Gibbs energy of mixing of two liquids to form an ideal solution can be calculated in the same way as we did for two gases. So the total Gibbs energy before mixing, so this is the I here, so Gibbs energy of our initial state is equal to the number of moles of component A times the chemical potential of A while it's pure, plus the number of moles of B times the chemical potential of B while it's pure. Again, this is before mixing, so our A is still pure, that's why we're using the chemical potential of pure A, and the B is still pure, we haven't mixed them together yet. And after mixing, now the individual chemical potentials are given by this equation, so the chemical potential of A in the liquid phase is equal to the chemical potential of A while it's pure in the liquid phase plus RT times the natural log of the mole fraction of A in our mixture, and a similar expression for B. So this means now the total Gibbs energy after mixing, and here now we're going to drop the designation of the liquid phase here. So the final Gibbs energy, GF, is equal to the number of moles of A times the chemical potential of A while it's pure plus R times T times the natural log of the mole fraction of A plus the number of moles of B times the quantity chemical potential of B while it's pure plus R times T times the natural log of the chemical potential of B. And this means that the Gibbs energy of mixing, so delta G mix, is GF minus GI. So this means that now our Gibbs energy of mixing is nRT times mole fraction of A times the natural log of A plus the mole fraction of B times the natural log of B. Again, where N here is the total number of moles, so the number of moles of A plus the number of moles of B. And just like for the mixing of ideal gases, the entropy of mixing for an ideal solution looks like this. So now we have the entropy of mixing is equal to minus N times R times mole fraction of A times natural log of mole fraction of A plus the mole fraction of B times the natural log of mole fraction of B. And this means that our entropy of mixing is 0. So let's figure out why. So we know that the entropy of mixing is equal to the Gibbs energy of mixing plus T times the Gibbs, the entropy of mixing. And the Gibbs energy of mixing is this quantity. And the entropy of mixing is the stuff in brackets here. And then we still need to multiply by T. So now everything in the brackets here times T is just the negative of all the stuff in the red brackets on top. So now we have nRT times our chi A natural log of chi A plus chi B times natural log of chi B minus that same quantity, and so it all goes away and we're left with 0. So for an ideal solution, the enthalpy of mixing is 0. So the change in volume of mixing, or the change in volume upon mixing, for an ideal solution can also be calculated. So we know that the change in Gibbs energy is equal to VdP minus SdT. And this means now that the volume is equal to the change in Gibbs energy with respect to pressure at constant temperature. So if we hold temperature constant, then the volume is the slope of dG over dP. So this means that now the change in volume of mixing is the partial derivative with respect to pressure of delta G mix, so the Gibbs energy of mixing, keeping the temperature constant. And for an ideal solution, the change in our Gibbs energy of mixing with respect to pressure, keeping temperature constant, is 0. And that means for an ideal solution, the change in volume upon mixing is 0. So our total volume before mixing, so volume of A plus volume of B, is equal to the total. That's the same before and after mixing for an ideal solution. Now, not all solutions are ideal, so this isn't always true. But for an ideal solution, this is true. So, note that the entropy of mixing for an ideal solution is the same as the expression for the entropy of mixing of ideal gases. And thus all the conclusions that we drew for the case of ideal gases will also fit here for ideal solutions. And this means that the driving force of mixing is the increase in entropy for the system. So, just like for gases, the reason why gases will mix spontaneously is that the entropy of is increasing when we mix them, the disorder is going up. The same is true for the liquid. As we mix two liquids, the entropy of our system is going up. And the entropy is the sole driving force for that mixing process. Note, however, that ideality means something very different for a solution than it does for a gas mixture. Right? In the gas, ideality means the molecules don't interact at all. For a liquid solution, for a solution, that's not what we mean when we say an ideal solution. So, again, in an ideal gas, there are no forces acting between the molecules. There are no intermolecular forces. But in an ideal solution, there are forces acting between the molecules, but the forces between the molecules, the AB forces, are identical to the forces acting on the molecules in the pure substances, so the AA and BB molecules. So again, this is why, if we have molecules that have similar structure, so if A and B are very similar structurally, then the AA and BB interactions are going to be fairly similar, and that also means that the AB interactions are going to be pretty similar to those interactions. If, on the other hand, A and B are very different structurally, then the AA interactions and BB interactions are going to be very different than the AB interactions, and our solution won't be ideal. So this is what we mean for an ideal solution. For an ideal solution, we can have huge intermolecular forces as long as they're no different than before mixing. Because before mixing in a liquid, we have intermolecular forces. Before mixing in a gas, we don't. Or at least that's what we're assuming for an ideal gas. We don't. Alright, so if the enthalpy change is large and positive, or if the entropy change is negative, because of a reorganization of the molecules, that results in an orderly mixture. So if we get more order in our molecules when we mix them, then the Gibbs energy of mixing might be positive. And in this case, the separation is spontaneous and the liquids are immiscible. So for, say, oil and water, alternately, the liquids might be partially miscible, or they might be miscible only a certain range of compositions. So it may be that if you have just a small amount of B dissolved in A, that they're totally miscible and you only have one phase. And it may be, or it may be that at mostly B and just a little bit of A, they're totally miscible and you can dissolve all of the A that you have in B. But it may be that in between, at say a 50-50 ratio, you may have two phases. One phase that is mostly A with a little bit of B, and another phase that is mostly B with a little bit of A dissolved in. And that's the case for something like oil and water. Oil and water do, in fact, mix, but the mole fraction of water in the oil is relatively small, and the mole fraction of the oil in the water is relatively small. So you have two different phases, one where water is the solvent and oil is the solute, and one phase where oil is the solvent and water is the solute. Alright, so the thermodynamic properties of real solutions can be expressed in terms of excess functions. And so we label those excess functions something to the E, right, with superscript E. So X here stands for, let's say, if it were entropy, it would be an S. If it were Gibbs energy, it would be a G, and so on. These excess functions are the differences between the observed thermodynamic function of mixing and the function for an ideal solution. So, for an ideal solution, the excess function is 0, because there is no difference, because it's ideal. But for a real solution, then we have some excess. So, we have whatever value we expected it to be if it was an ideal solution, but if it's not, what is the difference there? So that's our excess function here. So the excess entropy is defined like this. So the excess entropy is the entropy of mixing minus the entropy of mixing for the ideal solution. So this is the entropy of mixing of our real solution. So maybe I should write in real. This is the entropy of mixing for our actual solution minus the entropy of mixing for our ideal solution, what we expected the entropy of mixing to be. So if our solution is in fact ideal, or really close to it, then our entropy of mixing for the actual value that we get is the same as our ideal. So we have some value here. Well, that's the same value as our ideal value. So the difference there is 0. Right. So excess enthalpy and volume are both equal to the observed enthalpy and volume of mixing, because the enthalpy and volume of mixing for an ideal solution are 0. Okay. Remember, we already showed earlier that the enthalpy of mixing was 0, and we also showed that the volume of mixing is 0. So the excess is whatever the change really is. So if it's not 0, the excess is all of that excess. Alright, so 2 examples of the dependence of molar properties on composition are listed here. So here we have the enthalpy, the excess enthalpy, and here we have the excess volume as a function of mole fraction. And here we have benzene, and here we have the mole fraction of tetrachloroethene. Alright, so you notice that the excess enthalpy starts out at 0 with a mole fraction of 0, because we have pure of our second substance. Over on this end, at a mole fraction of 1 for benzene, we have pure benzene. So the excess function there has to be 0, because if we have a pure substance, it has to be an ideal solution, because there's nothing else in there. So it's got to be ideal. And so in between we have some curve, and note that over here for our excess volume, we have initially a negative excess volume, and it goes back up to 0, and then we have a positive excess volume, and then again it returns back to 0. Right? It has to be at 0 at either end, either a mole fraction of 0 or a mole fraction of 1, because again, it's a pure substance is by definition an ideal solution, and it can't differ from ideality. All right, so in our first plot, we have benzene and cyclohexane, and they have a positive enthalpy of mixing. Right? All of our values in here are positive, except for the 2 endpoints, which means that our AB interactions are weaker than our AA and BB interactions, which means that it's more energetically favorable to have AA interactions and BB interactions than it is to have AB interactions. So interactions between benzene and cyclohexane. And this means that because our curve here is symmetric, this means that our AA and BB interactions are similar in magnitude. So the size of the AA interactions and the size of the BB interactions are roughly comparable, but the AB interactions are different. They are significantly different than the AA and BB interactions. And this isn't terribly surprising that our AA and BB interactions are that different, because again, our two substances are benzene and cyclohexane. Benzene should react with other benzene about the same as hexane, cyclohexane interacts with other cyclohexane molecules. Right? But between the two, benzene and cyclohexane, there can be some significant differences. So between the benzene molecules, we have that pi stacking. The stacking of the rings allows interactions between the plane of one benzene molecule and the plane of another benzene molecule. Whereas with the cyclohexane, it doesn't have that pi stacking mechanism to it. All right, so in our second graph that I showed earlier, in B, the excess volume of a mixture of tetrachloroethane and cyclopentane is plotted as a function of mole fraction of tetrachloroethene. So at high fractions of cyclopentane, so low mole fractions of tetrachloroethene, so on the left side here, our volume contracts as we add tetrachloroethene. Now note that if we're adding tetrachloroethene, the volume is still going to increase, but the total volume is dropping. Right? So that's what we really mean here. The total volume is dropping. As we add the tetrachloroethene, because now the cyclopentane has an inefficient packing structure, and so when we put our tetrachloroethene in, it's able to sit in some of the holes in our inefficient packing structure of cyclopentane. But then that means that when we get to the other side, when we get to mostly tetrachloroethene, now we're putting some of our cyclopentane into basically our mostly a matrix of tetrachloroethene, and now the volume is going to go up. And so, at our high mole fractions of tetrachloroethene, so on the right side, the volume is expanding as the cyclopentane is added, because the cyclopentane is disrupting our efficient packing structure of our mostly flat tetrachloroethene molecules. So, now let us examine the deviations of excess energies from zero as a measure of how non-ideal a solution is. So we need to now introduce our concept of a regular solution, a solution for which the excess enthalpy is non-zero, but excess entropy is zero. So the entropy of mixing is exactly what the ideal entropy of mixing would be, but the enthalpy of mixing is non-zero, because we expected it to be zero. So that's what we mean by a regular solution. Right, so we can think of a regular solution as one in which our molecules of each kind are interspersed randomly, but the magnitudes of the AB and AA and BB interactions are not the same. So it's not like we have two different phases going on, they're just interspersed randomly, but our interactions aren't similar in magnitude. So we can now suppose that the excess enthalpy can be calculated with this expression, where this symbol here, xi, is a dimensionless parameter that's a measure of the energy of AB interactions relative to the energies of AA and BB interactions. Right? So here we have the excess enthalpy is equal to the number of moles times our dimensionless quantity xi, times R times T times the mole fraction of A times the mole fraction of B. And so if we now plot the excess enthalpy as a function of mole fraction for different values of xi over here, so note that we have a xi of 0 here, -1 here, -2, 1, and 2. So with a negative xi, the mixing is exothermic, because now our AB interactions are stronger than the AA and BB interactions, and so when we mix our A and B molecules, we're forming some of these AB interactions as we're breaking some of the AA and BB interactions. But because these are stronger, we're giving off energy. So it's exothermic. So we have a negative enthalpy here. On the other hand, if we have positive xi, then the AB interactions are weaker. And if the AB interactions are weaker, then we're going to expend more energy breaking the AA and BB interactions than we get back by forming our AV interactions. And so now our enthalpy of mixing is going to be positive. It's going to be more positive the larger Xi gets. All right, so for a regular solution then, the excess entropy of mixing is 0. So the excess Gibbs energy is equal to the excess enthalpy. Because again, remember that G equals H minus Ts. So if we put deltas in here, delta G is equal to delta H minus T delta S. If delta S is 0 and the entropy of mixing is 0 for a regular solution, because that's how we defined a regular solution. So delta S is 0, so this quantity goes away, and now delta G is equal to delta H. Okay, so the excess Gibbs energy is equal to the excess enthalpy, and that means now we can say that the Gibbs energy of mixing is equal to N times R times T times the mole fraction of A times the natural log of the mole fraction of A plus the mole fraction of B, the natural log of the mole fraction of B plus psi times the mole fraction of A times the mole fraction of B. So note that for xi greater than 2, there are two minima separated by a maximum in this plot of Gibbs energy divided by nRT as a function of mole fraction of A. So here we have pure B, and over there we have pure A. And so note that the Gibbs energy of mixing here is 0 at our two extremes. And again, Gibbs energy of mixing should be 0 if we're going from a pure A or B to still pure A or B. Again, so note that for our for any xi greater than 2, we have two minima here. So for anything greater than 2, like for 2.5 or 3, we have two minima. So we've got a minimum value here and there, separated by a maximum value for our Gibbs energy of mixing. And this means that in these cases, the system will spontaneously separate into two phases with compositions equal to the compositions of the two minima. So if we look at, say, this curve for xi of 3, if we try to make a mixture that is 50-50, we won't get one phase with a mixture of 50-50. What we'll get is, we'll get one phase with a value of this mole fraction, and we'll get another phase with that mole fraction for its composition, and the ratio of each of those will depend on the ratio of the mole fraction that we have in the total composition. So note that this will even happen at xi of 2. We do have a slight rise here, and so we'll get a value here and there, wherever exactly in there the minima are. So, and this is happening because, again, the system wants to go to the lowest Gibbs energy it can. So it doesn't want to sit up here, regardless of whether that's a positive value, as it is for xi of 3, or still a negative value for 2.5. It can get lower than that by splitting and moving down this direction or that direction. Right? And so it will spontaneously form two phases. And this is what something like oil and water, what that mixture will do. We'll get two different phases. So now let's look at colligative properties. So let's look at the colligative properties of a solution, which are the lowering of vapor pressure, the elevation of our boiling point, and osmotic pressure. Note that there are some other colligative properties like the depression of freezing point, but we're not going to talk about that here. So for dilute solutions, the colligative properties depend upon the solute concentration, but not the identity of the solute. It only depends how much of the solute we have dissolved. And if it doesn't depend on the identity of the solute, then it doesn't really matter what the solute is. So we're really just looking at the total concentration of solute particles, not the specific identity of those particles. Right, so throughout this discussion of our colligative properties, we're going to assume that our solution, that our solute, is non-volatile. And if it's non-volatile, that means that it doesn't contribute to the vapor pressure. So we're assuming that our solute has a vapor pressure of 0. So sodium chloride or something like that. It's not something like water or benzene, something that has a significant vapor pressure. We're using something that has essentially 0 vapor pressure. So we're also going to assume that our solute does not dissolve in the solid solvent, which means that when our solution is frozen, our solvent separates from the solute. So during the process of freezing, we go from a solution where our solute is evenly distributed to a place, to a point at which, as we start to freeze, we're freezing the solvent, but we're not freezing the solute in that solvent. Right? As we freeze, we get a larger and larger section of our total container that is pure solvent frozen in the solid phase. Right? And our solute stays in the liquid phase, in the solution. Right. So, the colligative properties are arising from the reduction of the chemical potential of the liquid solvent as a result of adding the solute. So, for an ideal dilute solution, the reduction is from the chemical potential of A in its pure form to the chemical potential of A in its pure form plus R times T times the natural log of the mole fraction of A. So note that there is no change in the chemical potential of the vapor or of the chemical potential of the solvent because the solute is not part of these phases. Right? We assumed that so here for the chemical potential of the vapor, we assumed that our solute is non-volatile, so it's not in the vapor phase. So the chemical potential of our A in the vapor phase isn't changing because it's still pure. Likewise, the solvent that's frozen, so the solid solvent, is also pure because we're assuming that our solute is not dissolving in the solid. Okay, so as we see in this figure, the reduction in chemical potential for the pure liquid solvent to the solution leads to a lowering of the temperature at which the liquid-solid equilibrium occurs and an increase in the temperature at which the liquid-vapor equilibrium occurs. So we are elevating the boiling point and lowering the freezing point. So as we go from the solid, right, remember we're not changing the chemical potential of the solid, and we're also not changing the chemical potential of the vapor phase because we're assuming that our solute is non-volatile. So that means that this line doesn't change and that line doesn't change. But when we lower the chemical potential from the pure liquid to the chemical potential of the solution, we're lowering this line, we're pulling it down, which means that we have to be moving to the left on our solid curve. That intersection point has to be moving to the left. To the left is lower temperature. So we have to be depressing the freezing point. But simultaneously, we're also moving down, which means to the right, on our vapor curve, and or that point of intersection between the chemical potentials, which means that we're going to the right on the temperature axis, we're increasing the temperature. So the boiling point has to go up, the freezing point has to go down when we add our solute into our solvent, when we make our solution. Alright, so the lowering of chemical potential is not an enthalpy effect because it happens even in ideal solutions, right? Even if our interactions between A and B are the same as they are between A and B and B, even if those interactions are the same, we still have this effect going on. And that means that it can't be an enthalpy effect, it can't be an effect between the interactions of the intermolecular forces of the molecules, interactions between the molecules. It must be an entropy effect, which means that it must be an effect of going from pure A to some random distribution of B in A, right? An entropy effect. So as we go from here to there, this is a very highly ordered state. We have here vapor phase that is pure A. Here we have a liquid phase that is pure A. Here we have a vapor phase that is still pure A. But now we have a liquid phase that is no longer pure A. We have some B randomly distributed in there. That randomness is increasing the entropy, and that's the driving force, right? Is to increase the randomness of our solution. So the vapor pressure of the pure liquid reflects the tendency of the solution towards greater entropy. And that occurs if the liquid vaporizes. Right? As we go from just liquid in our container to some vapor in there, right? We know that the entropy of a liquid is less than the entropy of a gas, but the entropy of the liquid is higher than the entropy of the solid. Right? The solid is a very highly ordered state. The liquid is less ordered than the solid, but the gas is very, very disordered. Right? There's basically no order there at all. The molecules are bouncing around totally randomly. They're not interacting with each other at all. Well, that's what we're assuming for an ideal gas. So going from the liquid phase to the gas phase means that we're increasing the entropy. So that's why some of the liquid is vaporizing. So as we add a solute to the solution, the entropy of our solution is increasing because our solution is transforming from a highly ordered pure solvent state to a more random structure with solute and solvent molecules interspersed. And this means that now the entropy difference between the liquid phase and the gas phase is not as high for the solution, right? Because the solution here has a higher entropy than the pure solvent there, but the entropies of the gas phases, the vapor phases, are the same. Which means that now there's less of a driving force to vaporizing our solvent to go into the vapor phase. So that means that we should have a lower vapor pressure. So this increasing entropy of our solution lowers the change in entropy upon vaporization, going from the liquid to the vapor phase, so moving out. And this means that a higher temperature is necessary to get the same change in entropy. Higher temperature is needed to get the same vapor pressure. So we have to increase the boiling point. So likewise, a lower temperature is necessary to overcome the decrease in entropy upon freezing. So going from the very highly ordered solid phase to the liquid phase, well, we're going from a very highly ordered solid phase with none of the solute in it to a more disordered phase of the solution than it would be if the liquid phase was pure. So that means that now we have an even higher increase in entropy because we're going from pure solvent in the solid phase to not pure solvent in the liquid phase. That's going to be a higher change in entropy than from pure solvent in the solid phase to pure solvent in the liquid phase. That extra entropy gain of having the solute molecules dissolve means that we can melt our solid phase at a lower temperature. So, again, remember that we've assumed that our solute doesn't dissolve in the solid, right? And that's key, because if our solute does dissolve in the solid, then that effect won't be seen. Alright, so let's consider the equilibrium between the solvent vapor and the solvent in solution at 1 atmosphere. So we're at normal conditions, or at least normal pressures. So we'll denote the solvent as A and the solute as B. So A is our major component, B is our minor component. So the equilibrium is established at the temperature at which the chemical potentials of the solvent vapor and the solvent in solution are equal. Right? Equilibrium always occurs at the place where the chemical potentials are the same. So this means that the chemical potential of A in the gas phase, and remember it's pure A because we have none of our solute molecules in the gas phase, because it's non-volatile, is equal to, that chemical potential has to be equal to the chemical potential of A in solution, which is the chemical potential of A while it's pure in the liquid phase, plus R times T times the natural log of the mole fraction of A in the solution, so in the liquid phase. Alright, so now we can show that the presence of a solute at a mole fraction chi B leads to an increase in normal boiling point from T star to T star plus delta T. Right, so from whatever the boiling point was while it was pure, so that's T star, the star there, remember, is for the notation for pure, to that boiling point plus some change, where the change in boiling point is equal to K times the mole fraction of B, where K is equal to R times T star squared, divided by the enthalpy of vaporization. And so K is, typically, we consider this a constant for some solvent at some temperature. Right? So from the normal boiling point, because the normal boiling point of some solvent doesn't change, because the normal boiling point is at 1 atmosphere. So, note that this equation doesn't reference the identity of the solute. Right? All it references is the mole fraction of the solute, right? Chi B. Doesn't matter what Chi B is, and this enthalpy of vaporization is the enthalpy of vaporization of the solvent. There's nothing in here about the identity of the solute, so it doesn't matter what the solute is. So this means that the elevation of boiling point is a colligative property. Colligative property being something that only depends on how much stuff you have dissolved. It doesn't matter what that stuff is. Right? So just how many particles are dissolved. Note that if you have something like sodium chloride in water, if the sodium chloride will dissociate, you have 2 particles there. Right? So your concentrations are going to be double the sodium chloride concentration. The concentration of total dissolved particles is going to be double for sodium chloride. For something like magnesium chloride, the total dissolved particle concentration is 3 times the magnesium chloride concentration. So you need to be careful with your concentrations here. Alright, so the elevation of boiling point does depend on the properties of the solvent, the enthalpy of vaporization, and the normal boiling temperature. But, so this means that the larger the normal boiling point, the larger the elevation of boiling point. Because again, let's go back and take a look here. The larger T star is, the larger the normal boiling point is, the larger K is, and that means the larger that change in temperature is when we add our solute. Alright, so in practice, that equation is usually modified to use the molality of our substance B, which we denote as this lowercase b here, and we get this constant Kb. So Kb is the empirical boiling point. The B there is for boiling point, not for molality or for B, our solute. So this is the empirical boiling point constant of our solvent, and we basically go out and we measure what Kb is at different molalities of total molality of dissolved particles. Alright, so now let's look at the equilibrium between the pure solid solvent A and the solution with solute present at a mole fraction Chi B. So again, we have solid A, and that's pure, because again we're assuming that our solute B is not dissolving in the solid A. And then we have our solution, so we have our liquid A mixed with B. Right? So A is our solvent, B is our solute. Alright, so at the freezing point, again the chemical potentials are equal. Chemical potentials of the solvent, rather. So the chemical potential of A, when it's pure in the solid phase, because again it was pure in the solid phase there, has to be equal to the chemical potential of A in the mixture. And we know the chemical potential of A in the mixture is the chemical potential of A while it's pure in the liquid phase plus R times T times the natural log of the mole fraction of A. And that expression is similar to that for the vaporization process that we discussed earlier. So we can derive similar results. I'm not going to go through the derivation, but we get basically the same thing. Only here in this case the delta T is equal to this K prime, where K prime has a similar look to it, where now we've replaced the enthalpy of vaporization with the enthalpy of fusion. So, larger freezing point depressions are seen in solvents with low enthalpies of fusion and high freezing points. So again, in practice, we express our freezing point depression as a function of the molality of our solute. So we get delta T is equal to Kf, F for freezing point. This is, again, an empirical constant times B, the molality, the total molality of all the dissolved particles. Right? So if you mix, say, sodium chloride and magnesium chloride and sodium hydroxide, it's the total concentration of all the particles. So the sodium ions, the hydroxide ions, the chloride ions, the magnesium ions, those concentrations all added together. Right? Those all going to be here. Because again, it doesn't matter on the identity of B. Right? It just matters with the identity of the solvent, which is wrapped up in Kf. That's what it matters. That's what changes our temperature here. Alright, so the solubility is not a colligative property because it does vary with the identity of our solute, but it can be estimated using a lot of the same techniques we've used above, so we're going to discuss it here. Alright, so when a solid solute is in contact with a solvent, it dissolves until the solution is saturated. Right? So here we have some solid B in contact with some A, and some of the B migrates into solution until we saturate the solution. Okay? So saturation is a state of equilibrium, right? Because at that point we have some molecules of B going into the solution. We have some molecules of B from the solution going back into the solid phase. This is a state of equilibrium. It's a dynamic equilibrium. So here we have the undissolved solute in equilibrium with the dissolved solute, and that means that the chemical potentials of them must be the same. So note here we have the chemical potential of B in the solid phase while it's pure has to be equal to the chemical potential of B in solution. So chemical potentials of our pure undissolved solute, this guy, and our dissolved solute, this guy, have to be equal. And we also know that the chemical potential of our dissolved solute, the chemical potential of B in solution, is equal to the chemical potential of B while it's pure in the liquid phase, plus R times T times the natural log of B, natural log of the mole fraction of B. And this means that now we can set this guy here, and that still has to be equal to the chemical potential of B in solid phase and pure. So now we can show that the solubility of the solute depends on the temperature. And so we get an equation that looks something like this. So the natural log of the mole fraction of B is equal to the enthalpy of fusion of B divided by R times the quantity 1 over Tf minus 1 over T, where Tf is our normal freezing point of the solute, and T is the temperature of the solution, and the enthalpy of fusion here is the enthalpy of fusion of our solute. So over here, we have a plot of the solubility as a function of the fraction of the temperature to the normal freezing point of our solute. And note that our solubility decreases exponentially as the temperature is lowered below the melting point of the solute. So if we have T over T star of 1, there we have, if we're at T over T star of 1, we are at the melting point of the solute, in which case the solute is going to melt and go into the liquid phase. It will join the solvent. It will be 100% of it will be in the liquid phase. On the other hand, if we get way down here to a ratio of 0, well, we can't actually get to 0 because that means that we're at absolute 0. But if we were at absolute 0, none of our B would dissolve. So that means that at absolute 0, nothing will dissolve in your liquid, which is great. If you want to get pure solvent, get the absolute temperature, get your temperature down to absolute 0. But you can't do it. Alright, so also note that our solutes with low melting points and large enthalpies of fusion have low solubilities at normal temperatures. So if you have, if you are far below your normal melting point, you're going to get a relatively low solubility. And also, now here we have different values for the enthalpy. And so, alright, so note that this equation should be treated as an approximation because it does not depend upon the identity of the solvent. So it claims that the solubility of a solute in one solvent will be identical to the solubility in a different solvent, which we knew is not true. We know that sodium chloride is more soluble in water than it is in, say, benzene. Right? But this equation doesn't explain that. Right? This equation claims that it will be the same in both solvents. But we know that's not true. So this is just an approximation. Right. So now let's talk about osmosis. So, which is again one of our complicated properties. So osmosis is the spontaneous movement of a pure solvent into a solution separated from it by a semi-permeable membrane. A membrane that's permeable to the solvent but not to the solute. So let's look over here. So here we have, on the left, we have some pure solvent at some chemical potential. Right? Chemical potential of A star. Right? This is at some pressure, P. And over here, we have a solution. Now, in between, we have some semi-permeable membrane. We're allowing our solvent to go back and forth. It can move to the right, it can move to the left. Our solute has to stay on the right side, right? It can't move through our permeable membrane here. So, on this side, we have chemical potential of A at some pressure P plus pi. We'll get to pi in a minute. So, the osmotic pressure pi, that's the pi I was just talking about, is the pressure that must be applied to the solution to stop the influx of solvent. So generally, here the P, the pressure down, usually we leave this open to atmosphere. We don't have to though. And on this side, you still have the pressure from atmosphere pressing down, but now we put some additional pressure on. Right? We have to put additional pressure on the right side to stop solvent from moving in. Right? So, the measurement of what that pressure is called osmometry. So this is our determination of molar mass using the measurement of osmotic pressure. And we often use this to determine the molar masses of macromolecules, because for very, very large molecules with molar masses of 1,000 or more AMU, those molecules are really hard to measure the mass of the molar mass of in some other ways. It's really hard to stick these in, say, a mass spectrometer, because they don't volatilize. They're so big that we can't volatilize them, or if we do, they break apart into lots of tiny little chunks, and we just can't tell what the total mass is, because it's just been broken up so much. And so the osmosis is a very nice technique to use, because we can use it in, we can leave our solute in whatever solvent we want, as long as we have a semi-permeable membrane that allows our solvent to flow, but not our solute, not our macromolecule, and which means that it's a fairly gentle procedure. We don't have to heat it up, heat our macromolecule up. We don't have to vaporize it, get it into a vacuum or something like that. So it's a nice technique. So, at equilibrium, the chemical potentials of the pure solvent, that's this, must be equal to the chemical potential of the solvent in solution, that's this guy, which means that the chemical potential of our solvent in solution is lowered by the presence of our solute, but it can be restored back to its pure value by the application of this additional pressure. Right? So we can put additional pressure on, and that means that it gets back to the chemical potential that it had when it was pure. So, for dilute solutions, the osmotic pressure is given by the Van 't Hoff equation, which is here. So, pi is equal to this quantity B times R times T, where this B is the molar concentration, so the number of moles of B divided by V, the volume. So, again, the brackets there mean concentration of B. Right? B is our solute here. So that was the properties of solutions.